Hi everyone, welcome to our session in Monster Scale Summit. I'm Worakarn Isaratham from Agoda. Today I'm going to share with you how Agoda scale 50 times throughput with ScyllaDB, and let's start. So a little bit about myself first. I'm currently a lead software engineer working here at Agoda in Bangkok, Thailand for about 8 years. I've got some experience in distributed systems, data engineering, and software testing. So I first started out as a software tester, which led me to be more interested in software correctness and things like provably correct programs. So Dependable Software Systems was the name of the program I did my MSc, but that was a different story. Today, we're here to talk about scaling at Agoda. So I'm going to walk you through the feature store project in Agoda and how ScyllaDB is being used to support the project. I'll tell you about the capacity problem we had at one point and what solutions we tried. So first, let me briefly introduce you to Feature Store. What is Feature Store? Feature Store is a centralized repository that is specifically designed for managing and serving machine learning features. So in the context of machine learning, a feature is a measurable property or a characteristic of a data point that can be used as inputs to machine learning models. So Feature Store helps managing features across the entire machine learning pipeline, from data ingestion to model training to inference. So basically, we make it easier to work with the machine learning models, and this helps both our data scientists and data engineers alike. So why does this matter for Agoda? We are a digital travel platform, right? So some use cases are directly tied to our product. For example, we try to predict what users would like to see, which hotel would do well to the customers, what kind of promotions we should serve, and so on. And also on the more technical side of things, we have used it in stuff like bot detection, for example. The model would use traffic patterns to predict if a particular user is a bot or not. And if it is, then we can take appropriate actions, like block them off or at least deprioritize their request, right? So yeah, Feature Store is essential for both products and engineering at Agoda. In Agoda, we have our own in-house Feature Store. So as you can see in this diagram, roughly this can be split into three areas. First, on the left-hand side, there's streaming features generation. That's a tool to help creating features easily from our internal Kafka data streams. Features would be generated and stored in centralized database. So we have, like in the middle, we have the offline store, where users can look at the past historical feature values to train new and better models. And most importantly for this talk is the online store, which only store the latest feature values that are used in production in real time. So this part has to be like really, really fast. So that's one of the reasons why we choose ScyllaDB to back it up. So we are currently serving about 3.5 million entities per second to our users. So that's what the EPS stands for, entities per second. It's the unit we use to measure our throughput. So that's 3.5 million entities per second coming into our client SDK, which we provide in Scala and Python version. And about half the features are served from cache within the client, right? So that's like 1.7 million entities per second reaching our application servers, which is written in Rust, running in our internal Kubernetes pods in what we call internally a private cloud. And from the app servers, we would check first if the features already exist in the cache. So we use DragonflyDB set up as a non-persistent centralized cache. So if it's not in the cache, then we go to ScyllaDB, our source of truth. So our ScyllaDB cluster is a model setup with just 6 nodes of bare metal servers. We have set it up identically in 4 different data centers. And across all 4 DCs, ScyllaDB is right now serving about 200K entities per second. So we do all of this while maintaining service level at 10 milliseconds P99. In reality, we are a little faster than that. So the servers respond in about 5 milliseconds, and our client would get a response time of about 8 milliseconds at P99. So here's a look at how our traffic has grown since the start of 2023. That's about 2 years ago. So in this graph, we are looking at the traffic to the application servers, not the database. This is the application servers. It captures the growth on our BCSDC. So that's like I said that we are serving 1.7 million entity per second, right, from the servers. That was for all 4 DCs. Here we are only looking at this one BCSDC, and we are getting more than 600K entities per second. So this is a growth of 50 times from where we were 2 years ago. Now, this graph, we look at the traffic that reached ScyllaDB. So currently we are serving 60K entities per second from this BCSDC. So it has grown, but only by 10 times. That's more than 50, right? But that's because our cache are also getting better with time. So the cache hit rate has improved as well. Yeah, we've grown by 10 times, but it's not been exactly a smooth experience. At one point, we got a major capacity problem. So that's right about here. That was around mid of 2023. So at that point, we were getting about 10K entities per second. And then there was this new user who wanted to onboard to Feature Store. So that traffic presented a very problematic situation for us. So first, they have a very bursty pattern. So what I mean is that usually they only make a small amount of requests, but then all of a sudden they would make this big flood of requests based on some external signal, right? So they would ask for entities that they have never requested before, and our cache could not help us. So this is a situation that we call cold cache scenario. All the cache would fail, all the traffic would hit Scylla most directly, and this burst would hit us at 120K entities per second. And to remind you, that was like 12 times of the 10K load we had back then. And even if we compare to now, that's still twice the load we are having now 2 years later, right? So it was a huge amount of load. Bursty traffic, so that was one problem. Another is that the burst consists of a lot of duplicated requests in a very quick succession. So imagine you have 10 identical requests coming in. You would expect that the first request would hit the database, right? But the other 9 should be reading from cache. But because all 10 requests come at the same time, the first request doesn't even have the time to fill the cache yet. So all 10 requests concurrently hit the database. So this is a phenomenon known as cache stampede or dogpiling. Another pattern that makes it hard for us is that they would keep trying any failed requests until success. So it's not like we can just block them off, right? Because they would keep coming back. So we were put under stress for a long period. So we knew that we've got a capacity problem with this new traffic hit us on 2 DCs. So one interesting thing is that while one DC was totally crippled, the other one was relatively healthy. Well, it's also slowed down, but 10 millisecond SLA was definitely breached, but more or less it survived without that much errors. On the bad DC, we got very high error rates, and it took very long to complete all those retry attempts. It took 40 minutes to complete everything, while on the good DC, it took only like 1 or 2 minutes. So we look at the metrics and we found, like as we show on the right here, we are seeing that ScyllaDB read latency was very high, right? We are seeing the latency in terms of seconds here, where normally it would be sub-seconds, like a few milliseconds. So yeah, we've got some clue, right? ScyllaDB was very slow, but only in one DC, not in the other. So there must be some difference in the setup. So we look at and compare the setup, right, and found that these were the difference. So on the bad DC, we were using SATA SSD, while on the good one, we use NVMe SSD. So SATA was already quite old technology even 2 years ago, right? So yeah, so we did some speed test and estimate that replacing the disk should give us some 10 times boost on the read side. And although we were more concerned about read here, our traffic still contains sizable amount of write as well. So the better write rates, as you can see here, would be very welcome. Okay, cool. So we had identified the problem with the disk. Should we just go out and buy a new disk and call it a day? Well, yes, we ordered a new disk right away, but it would still be months away before we could get our hands on what we order. And we need to survive somehow in the meantime. So we did some capacity tests and make some linear projections on the traffic growth. And we realized that even without this new load, we could only survive for about 8 or 9 months before hitting the capacity limit. And with the new load, we had even much less time than that 8-9 months estimation. So we got to working with the users and try stuff like more aggressive caching from the client side, and cutting out unnecessary requests and spreading out the burst a little bit to flatten the peak, right? So with all of that, we managed to limit the new load to 7K instead of 120K. So we could go ahead with this new load for the moment, but still, it wasn't a reassuring situation, right? We knew we were close to reaching capacity already, and we need to do something to survive while we were still running with SATA disk. So we got a few ideas that we would like to try and see if it improves our capacity. But before that, we need a good baseline first. Right? So the capacity numbers from the previous slide, that was from real-world traffic. But there are some caching effects included since ScyllaDB also used their internal cache and mem table to enhance the read performance. But we want to target this more directly, right, since we want to tackle this cold cache scenario. So what we did is to try to avoid the caching as much as we can. Right? And that's done by creating this artificial load with a special one-time use test entities. We also specify bypass cache in the query, flash the cache before and after every test run. Right? So yeah, with all of those, we got the baseline read capacity on the bad DC to be at 5K entities per second. Okay, now we've got the baseline. We are ready to test out the ideas. So the first one is about different data modeling. So the model we've been using is to store all features from all the feature sets. So a feature set is just a collection of related features, right? So we store all of them in a single table. Using one table makes it easy to onboard new feature sets, as we never need to create new tables. But the downside is that it's very hard to remove unused features. So we ended up with quite a bit of outdated features in the table, and this might have some performance effect. But the idea here is more about data locality, since features from the same feature set are always retrieved together in the same query in our design. So we were hoping that by organizing the features by feature set and by making it one table per feature set, it might help with better locality and hopefully lead to better read latency. But the result is, as you can see here, it makes no difference. In hindsight, this non-improvement is probably because we were already partitioning the data by feature sets and entities. So this was more or less the same physical setup, but with a different logical organization. It makes sense that we didn't see any improvement here. So we move on to the next idea about compaction strategy. So if you go to the documentation, there'll be a section that recommends a compaction strategy based on read and write distribution of the workload. Our workload is classified as read mostly in many updates. So we chose size tier strategy as per the recommendation. And I think the reason this is recommended is because the many updates part that can create write amplification, right? So if we go with level compaction, it could have some bad effect. But we knew that we were having this slow read problems, and we wanted to prioritize read latency. And also from one of our tests, we saw that just trying to fetch 1 kilobyte of data, it would require reading 70 kilobytes from the disk, and that read include stuff like SSTable index. So upon further inspection, we noticed that our SSTable files are very large, like even larger than our data files. So minimizing the number of SSTable reads is a plus. So all of that means that level compaction at least is something that we're testing to see what kind of benefits we would get if we make the switch. And yes, we've got some 50% improvement, so that's some good news. We still got one more idea, and that is to increase the summary file size. So ScyllaDB used summary files to help navigate to index files, kind of like another layer of indexing. So size of summary file is controlled by this configuration, SSTable summary ratio. So our thought was that by setting the ratio to a higher value, we would have a larger summary file, which means a more efficient indexing and hopefully less amount of this I/O. So we tuned it up by 20 times. And that turned out to be quite effective. So we got up to 20K entities per second. That's 4 times improvement from where we started. And this is also easy enough to apply. So we actually roll it out right away. And then a few months later, the NVMe disk that we ordered arrived, right? And it blew everything else out of proportion. So we got up to 300K entities per second. That's 50, 60 times improvements. That's huge. So here's how we roll these improvements out. I already said that the new summary ratio was applied right away, and that gave us some breathing room with 2-3 times more capacity. And then 3 months later, we've got this NVMe disk, right? That moved us into 50 times more capacity. You might notice that we haven't applied level compaction strategy. So there are 2 reasons for that. First is that the compaction strategy settings only apply to new tables, which means it needs data migration. Second is that NVMe were already put that in a very good position, so there's no need to risk creating write amplification that would come with level compaction. And since we were no longer at any immediate risk anytime soon, we started to shift our focus to improve other parts of features though. For example, we improved our caching. We did rewrite our application code in Rust. And we also try some cache stampede prevention mechanism to reduce load coming to ScyllaDB. Of course, it doesn't mean that we completely neglect ScyllaDB. We still come back to it from time to time with new ideas. For example, first one here, this is some recent experiments we did. So the first one is an attempt at different partitioning. We try to switch from partitioning by feature set and entity to partition by just feature set alone and cluster by entity. And the result was so bad, it got 400 times worse. So this idea was shelved quickly. But another idea is to change the data model. So right now we store 1 row in ScyllaDB per features. But as I already touched on a little bit, we always get all the features from the same entity together. So there's actually no benefit from having the features in separate rows. So what if we move them all into a single row, like in this diagram, that's 3 rows of features. So if we squash them into 1 row and we measure the improvement and we got some 35% improvement. So yeah, this is a good one, but it's required data table migration. So we'll keep this idea and apply it when eventually we do the migration. Okay, so what have we learned from all of this? I would say that while we've been using ScyllaDB from very early on, we had not really used it to its full potential since we did not set it up correctly. Only after we made all these changes, using fast disk, made our benchmark, know our capacity, right? Design our data models to match the needs. This is all basic stuff, but it's very important to get the basics right. And so only after all of this that we can say that we are properly using ScyllaDB up to its potential. And that's how ScyllaDB has helped us to achieve our 50 times scaling. So that's all I want to say. Thank you very much for listening. And if you have any more questions, if you want to know more about this, you can contact me at these addresses. And yeah, thank you for your time and enjoy the rest of this summit.